Hello everyone, my name is Mark Prandolini and I work at the University of Hamburg. I'm also co-founder of the laser firm Class 5 Photonics. So today I want to present a review of thermal parameters of lithium-based nonlinear crystals for high power 8 micron sources. This work was done in collaboration with DAISY, a Helmholtz Institute. So why might you need high average power? By high average power, 8 micrometers, I mean over 1 watt and repetition rates over 100 kilohertz. So the obvious example one might think of is imaging, where you need sufficient pulse energy to provide sufficient signal to noise at each pixel. And then you need to scan across the whole image. This takes time. Other applications requiring high power would be 2D mid-IR spectroscopy and high average power HHG attosecond sources. So that's why you might need high power. So I'd like to now discuss a little bit about the technology we use at Class 5 Photonics, which is OPCPA, which stands for Optical Parametric Chirp Pulse Amplification. Now, the optical parametric amplification part is closely related to difference frequency generation. So this technology offers broadband amplification, has minimal heat dissipation compared to conventional lasers, is tunable, and has a high gain in a single pass. That means our lasers are compact. And the idler wave is also CEP preserving. Now, just to sort of explain why conventional lasers have larger thermal loads compared to optical parametric amplifiers, in a conventional laser, the pump pumps electrons into an excited state. Therefore, the lasing material stores energy. These electrons decay to the laser transition. This decay gives off heat. As opposed to an optical parametric amplifier, no heat is stored in the crystal. The energy of the pump wave is given to the signal and idler waves via a second order process. So there's no heat stored in the crystal. However, there is a small amount of linear and 2-photon absorption, which I will come to later. Finally, the DFG equation is the idler frequency equal to the pump frequency minus the signal frequency. So that introduces the technology and some of the terminology used in this. So I'd like to go over now a bit about the design, the rough design of our OPCPA DFG efficient compact mid-IR laser. We begin with a commercial ytterbium YAG laser system with an output of 1 micrometer. You can get them anywhere from 0.25 to 1 picosecond with under 100 watts into well over 1 kilowatt. They come in 3 varieties: InnoSlab, thin disc, and fiber. And Class 5 will help you with the decision which is appropriate for your application needs. So the heart of the system is a single DFG stage, with inputs directly from the pump laser and from a white dwarf laser from Class 5 Photonics with an output of 1.14 to 1.13 micrometers. These 2 waves are combined together in the DFG crystal to produce an idler mid-IR wave between 4 and 11 micrometers, again, tunable. Now, as you can see, I've presented 3 beam splitters. The first 2 are conventional, and the second one separates out the closely related 1 micron pump and the closely related 1 micron or close to 1 micron seed signals compared to the mid-IR between 4 and 11 micrometers. This beam splitter is quite tricky and requires special technology from class 5 photonics. Finally, when I talk about efficiency in this talk, I mean that the initial pump energy compared to the final output mid-IR energy after all the beam splitters. Okay, so as I mentioned previously, the heart of the system, or the critical stage of the system, is a single DFG crystal, combining the pump and signal waves, producing an idler wave. Now, it turns out, in most cases, it's the pump wave that causes most of the heat. So class 5 photonics, together with our partners at DAISY, decided to do a design study of the critical lithium-based nonlinear crystals for high power mid-IR applications. Now, on the left-hand side, I've got an experimental setup that we used. We had available a 200-watt ytterbium YAG slab laser from Amphos. We developed a thermal imaging method to measure the nonlinear and linear absorptions, and used a Basel camera to measure the nonlinear refractive index. So let me summarize now the key results. In red, as you can see, I've presented the best result, which was from the LGS crystal. It has the largest band gap, sufficiently good D effective, very good thermal conductivity, and low linear and 2-photon absorption, with also a low nonlinear refractive index. It also has the highest laser damage threshold. This is the best crystal for broadband applications. Another crystal that you might want to consider is LIS, which would be very good for narrowband tunable applications. So let me present some of our key results from our laser design. As I mentioned before, we started with a 200-watt ytterbium YAG slab laser. We scaled it down to 40 watts and achieved the following tuning curve, from 4 to 11 micrometers, and a broadband signal between 8 and 9 micrometers. Now, over most of this range, we achieved pulse energies above 1 microjoule. And between 8 and 9 micrometers, efficiencies got over 1%. Now, the dip you see between 6 and 7 micrometers is due to water vapor, and this can be eliminated by purging the system with nitrogen or an inert gas. So if I now concentrate at that pulse at 9 micrometers, pumped at 40 watts at 1 micrometer, we achieved 440 milliwatts at 9 micrometers. Pulse energies of 2.2 microjoules at 200 kilohertz, efficiencies at 1.1%, and the spectrum you see there has a Fourier limit of 68 femtoseconds. So now let's talk a little bit about dispersion management at 9 micrometers. At 9 micrometers, it's a little tricky to do dispersion management. There are a lot more dispersion tools available at lower wavelengths. However, you can find materials with both positive and negative second-order dispersion at 9 micrometers. So second-order dispersion is no problems. However, almost all materials have positive third-order dispersion at 9 micrometers, and this third-order term has to be addressed. So Class 5 addressed this problem using chirp mirrors within our white dwarf laser producing the seed signal. And if the chirp mirrors are chosen correctly, you can roughly eliminate third-order dispersion, as shown by our cross-correlation measurement on the left-hand side, with a near-perfect Gaussian fit. So a deconvolution of the cross-correlation reveals a pulse duration of 79 femtoseconds from our spectrum that you saw previously with a Fourier limit of 68 femtoseconds. And finally, I'd like to go a little bit more into what are the power limits at 9 micrometers. Now, as I mentioned previously, we did a material study at 200 watts using the full power, and we listed all the critical thermal and optical parameters. So if we were to use the 200 watt slab laser, we expect to see 2.2 watts at 9 micrometers, pulse energies of 2.2 microjoules at 1 megahertz, and pulse durations to remain under 100 femtoseconds. Well, I hope you enjoyed this talk and got some insight into what we are doing concerning our mid-IR project at Class 5, photonics. The system I presented to you is just one example, and we're happy to meet your particular application needs. So if you want to know more, please get in contact with us or get in contact with me directly. I thank you for your attention.